Can you guys hear me on Zoom? Zoom people, can you hear me? Nice, nice. So, hello everybody. Welcome to this first workshop in the series called Learning Machine Learning, presented by DSC at UC Davis. My name is Shyam Agarwal, and with me are my fellow presenters, Jeevu Lee, Yash Anani, and Khalil Buckley. So today, firstly, we'll talk about some basic machine learning models. And this Saturday, we have our second part of the workshop. We'll build upon this knowledge, talk about some neural networks, and ultimately the final goal is to create a handwritten digit recognizer. So let's get started. Before we talk about what machine learning, like the basic models of machine learning, let's just talk about what machine learning is. There's a common confusion among people that artificial intelligence is equal to machine learning. But this is not true at all. Artificial intelligence refers to anything that is aimed at making machines smarter or giving them human-like capabilities, because we do consider that humans are the smartest species in the world. But machine learning is a very small subset of artificial intelligence. Machine learning basically refers to any AI system that has the capability of self-learning or learning without explicitly being programmed. What I mean when I say this, it's very similar to how we learn from our experiences. When we were very small, we didn't know that we shouldn't touch hot objects. But when we felt the same pain multiple times, we realized from our experience that this is a task that we shouldn't do. This is something similar which happens in a machine. We kind of expose the machine to a scenario or a situation and let it kind of explore the scenario, understand what the truth is, and then we can give it some unknown scenario and ask it to predict what is going to happen. Now let's be a little more concrete about what I mean when I say this. And let's take a simple example. Let's say we are working in a grocery store and we have been given the task of separating apples from bananas. So let's say we have like a very huge pile of fruits and we want to find which one is an apple, which was a banana. And definitely we are all very smart humans. We don't want to do this labor work on our own. And that's why we decided to train a machine to do this. Firstly, can somebody tell me what's a feature or like a characteristic which kind of distinguishes apple from bananas? And note that I'm talking about the term feature in a colloquial sense, but that's the exact machine learning terminology that we use. Anybody? That's a good one. Anybody else? Yeah, there are like plenty of them, right? Shape, size, length, weight, color. Just for simplicity, I'm talking about two particular of them. One is color and one is hardness. So now what we do is we go ahead, collect like 50 apples, 50 bananas, make this very huge chart of like my color, my hardness, and then what's the actual fruit. Like I measure color and like make this chart and tell that this is an apple, this is a banana, banana, apple, banana, and just feed this into my machine. Now we call this thing as our training data, because we are firstly training the machine by giving it exposure to the scenario that it wants to learn about. Now, what does the machine do with this? We told the machine that, see, there are two things that the answer depends on. One is color, one is hardness. So firstly, it looks at a fruit, makes kind of a random guess or something, and then it sees what's the actual result. And with multiple iterations, it tries to understand how to get closer to the actual result on its own. Now I want to consider like two specific scenarios over here. The very first scenario is, what if the machine sees a very unripe greenish color banana? We all know that unripe bananas are hard, right? So maybe what my machine has in its mind over here is, we can think of something like a beam balance. And maybe my machine thinks that hardness is something that is more important than my color. Now, when it will see that green banana, it would think that, oh, it's hard, so it's apple, and it will conclude the answer to be apple. But then it would realize that the actual answer was banana. So now what it does is, it kind of rescales this weighing balance to bring hardness little up and color little down. But how much amount of like rescaling should happen? So let's say maybe my machine made color very more important, and like hardness very less important, then I'm pretty sure one of my observations would be something like a yellowish apple or probably a rotten brownish colored banana. So now my machine would again make a give a wrong result, and then it will again rescale this balance. So this kind of tells us that as the amount of data increases, my machine will be able to like make these balances and like rescale how much importance it's giving to each of these parameters. And like it might seem to be like very easy and kind of like, oh yeah, that's obvious kind of an idea, but this is the central kind of thought process behind machine learning of like weights. And like the technical term is weights, and it basically means how important is a particular feature. And the entire process that I just talked about, that's something very similar that Facebook does when you post pictures, right? It has a lot of training data when you tell it that it's your picture, and once it finds such a picture of yours and like it predicts, it just tells you about that. And this is very similar to what we'll be doing this Saturday. We'll be making our own handwritten digit recognizer, which will do something similar. Yeah. So now let's actually talk about some coding thing. And I want to show you guys how to like make basic plots and like, because it's very important for our data analysis. So currently I'm using Google Colab. The reason we're using Google Colab is that we don't want everybody to like download a particular IDE for the workshop. So Google Colab is like a Google product where you can write and execute Python code. No need to like download it. It's a web IDE. So I guess I can maybe wait for like a minute so that everybody can open Google Colab.
I mean, if you need help later on.
Yeah, and if you guys need any help, just raise your hand, and like Zoom people can also raise their hand, and we'd be happy to help. Sure. And I'll not be writing many comments while explaining, because we'll be sharing the code template later on. But we do suggest to like kind of write along with us so that you don't fall behind. Okay, so assuming that everybody is with me, I'm starting. So currently what I'm doing is I'm importing matplotlib.pyplot as PLT. So matplotlib is a library in Python which is used for like interactive visualization. So like you can make different kinds of plots like bar plots, histograms, scatter plots, and things like that. Let me say my x is I for I in range 10. And let's say my y is equal to and I'm just printing my x values and my y values to see what we want. Now, in order to make a plot, it's very simple. All we need to do is say plt.plot x comma y. And we have our plot with us. Now, if in case you want to attach something like a x label, you can do that, let's say x-axis. And then plt dot, if you want a y label, we can do that by saying y-axis. We do have x-axis and y-axis here. If we want to make some other kind of plot, we can, let's say plt dot scatter x comma y, and we have a scatter plot. Oh, sure. Is everybody good? Okay. So now earlier I was talking about this particular thing where we had like feeded this entire data into my machine. But how do we get the data for our experiments right now? So basically, maybe you have a file which has all the data downloaded with you. Then you can use some function like read CSV to read that file. But what we are doing right now is the workshop is basically based on sklearn, which is a library in Python, which is kind of specifically aimed towards machine learning. So sklearn offers us a lot of data sets, and we'll be seeing one of them. So this is kind of a very popular data set in machine learning, which is called iris data set. So what I'll do is, from my data sets, I would call load. And if you just pause over here, spelling is wrong. If you just pause over here, you'll see that it gives you a lot of options. Like there are so many data sets over here, and we are just choosing one of them. So maybe once you learn a model and you want to try it and test it with some other data set, you can just change this to get another data set. So I just loaded my iris data set. There's one more thing by convention, that the features are labeled as capital X, and the labels, which is like apple, banana, or whatever we are classifying, is labeled as small y. So I'm just following that convention over here. So I would say iris dataset dot data, and then iris dataset dot target. Now, first of all, we need to see how large is my data set. So what I can do is I can just say print capital X dot shape, and then I can say print small y dot shape, and let's just see what's the output. Okay, so we see that X is an array of like 150 by 4, and Y is an array of 150 by 1. Does anybody have any idea what this means? Any guesses or any trend? Okay, so basically my data that is similar to the hardness and the color that I was giving the machine. It says 150 by 4. So basically I have like 150 observations, and for each observation I have 4 input data points, and what I'm getting as an output is one particular output. So I just have like these 150 values, like 150 comma nothing basically means 150 by 1. Now definitely we are curious to know what this data looks like and what it is. So let me just print the target names, like what are my labels, and then I can also print one of the members of my array. We all know that array start from 0, right? So just printing the first one. Wait. Oh, sorry. This should be iris data set. Okay. So firstly, I don't pretend to know much about biology, but that's all I know, that these 3 are some plant species: Setosa, versicolor, and virginica. And the data points, these 4 numbers, are basically, I can just write a quick comment about that. The first one is the sepal length in centimeters. The second one is the sepal width in centimeters. The third one is the petal length in centimeters. And the fourth one is the petal width in centimeters. So this is how my data looks like. I have these 4 values, and we are trying to predict if something is which species does a particular thing belong to. Now the last thing about this like plotting and data analysis thing that I want to talk about is a particular function which I'm importing from sklearn dot model selection. It is called test train. Oh, wait. Firstly we train and then we test. So train, test, split. What I can do is I can create some variables, say x train, x test, y train, and y test. So basically the idea over here is that when I collected that data, I trained my machine. But what's the proof that my machine learned everything, right? After training my machine, I need to test that is the machine giving me right predictions, and then I should measure the accuracy. And if the accuracy is well beyond my expectations, then only I can use it in the grocery store, right? Otherwise, I lose my job. So what we can do is we can make these 4 variables: x train, x test, y train, y test. And sklearn makes it so simple for us. We can just call this function, pass our features are labeled, and then give it something called test size. So basically the general idea is that we want to train on data that is more than the amount of data, the data that we are testing on, because as I just mentioned, that the larger the sample you train the data on, the more the accuracy you have, right? So maybe just like a random number, I'm just saying that my test size is 0.3, which basically means 30%, like allocate 30% of the data for testing and the rest of the data for training. And we'll see the use of this when we'll talk about some actual models right now. So yeah.
Right. Yeah, what's your question?
Oh, wait, I can see that. Okay, you can go ahead.
All right, so let's go over how the KNN algorithm works. So I want you to follow along here as I'm writing it.
You can just continue. I'll just respond to chat.
All right, so basically, we're going to go through how the KNN algorithm works. So this is basically a classification algorithm, a very classic machine learning or AI algorithm. And what it does is it's basically to help you classify what a new object is. And how this works is you're going to have your graph, like Shyam was showing you earlier. Let's say you have the two features. You have the hardness on the left. And let's say you have the color on the bottom. And for this example, let's say we have like apples. So let's say all the apple data points are going to congregate somewhat here. And let's say we have bananas. Banana data points are going to congregate here as well. And let's just imagine that our data is going to look like this. So basically, when we collect apples, when we collect bananas, we see that, hey, bananas generally have a different color because they're on, this side of the graph, right? And they have a different level of hardness and so on and so forth. And we're going to take this data and look at it, right? What we're going to notice is that the KNN algorithm is going to say, hey, we have this new object here labeled as C. And what it's going to do is it's going to zoom in on this object. C. It's going to say, okay, I have one apple here. And I have two bananas here. The reason why it's going to look at three objects is because in this case, we're using K set to 3. And KNN stands for K nearest neighbor algorithm. So K nearest neighbor algorithm set to 3. When K is equal to 3, that means we take 3 objects that are closest in distance to our C, to our new object, see? And so the reason why we do that is because we're trying to classify what C is. And so in this case, what's going to happen is the algorithm is going to say, hey, I have one apple and I have two bananas that are closest in distance to this new object C. Therefore, I'm going to look at C and say that C is a banana. Are there any questions so far? Does everyone understand how that works? So one major pit. Oh,
So it's just a singular nearest thing.
it's going to look at the distance. Yeah, so it's going to It's gonna
Considering just one or
one or two what?
two, two different bananas, but what if it was closest to apple, even though it's two?
Well, what it's basically doing is it's saying I need to look at three nearest neighbors, right? Because k is set to 3. And then what it does is it locates this circle here and it says, oh, these are the three nearest neighbors to this new object. Supposedly, we don't know what it is yet, right? And then from there, it says, oh, I have 2 bananas and 1 apple. Therefore, since I'm around more bananas than apples, I'm a banana. You understand?
Yeah.
Okay. So basically, some major pitfalls to locate during this is that if you have a set of 2 classes, or sorry, if you have an odd value of k for a 2-class problem, that's what's basically going to work best in this kind of algorithm. And in the case of this algorithm, what I mean by that is, let me just write it down for you guys. Sorry. That basically means that, like, let's say that we have C here, we have 2 apples here, and let's say that we chose k equal to 4. Let's say we chose k equal to 4. That basically means that we're going to have a problem because we don't exactly know what C is. And so in this case, we need to choose an odd value for k. So if k is equal to 3, like we had last time, we're going to be able to erase one of these, choose only the 3 nearest, and then locate C and see that it's a banana. So that's the major thing to observe. And then also the KNN algorithm has a poor time complexity. Because it needs to calculate the distance of the nearby objects. So basically what that's saying is that it's a very slow algorithm, but it's still very one of the most widely utilized ones. So that's why we're learning about it.
So let's code right now. How will we code the we will code KNN model right now. So for this first, we are going to import some libraries. So from sklearn dot neighbors, we're going to import KNeighbors classifier. Yeah. All right, check it's fine or not. Let's go. So now we have to create a model. For this, we'll create a model named KNN. We'll create KNeighbors. We're going to use the KNeighbors classifier to create a model. Now we're going to create the number of neighbors. Yeah. Does anyone want to give me a number for the neighbors? Any number? 5? Okay. And yeah. And now I'm gonna train the model. Since we have already formed the testing and the training set. Now I'm gonna train the model with the training set, and I'm gonna do. Now basically train the model. Now I'm gonna use it to create some predictions. So let's try printing all the predictions. Oh, Oh wait, yeah, sorry, I wrote the name wrong. It's like a normal. Yeah. So now I've got all the predictions. Now, as you can see, these predictions are in form of numbers. So these numbers represent the all the classes we saw above, which are here. Setosa, versicolor, and virginica. So for the 0 represents the Setosa, 1 represents the versicolor, and the virginica is represented by 2. Now we have the predictions. Now we have the predictions, but we don't know if it's accurate or not. So let's check for its accuracy. So there's a metric system where we can use it to check the accuracy of our code. Check it's correct. SQ.
Metric.
MERA.
Not metric. It's metric.
TRI, not TER.
And now we're going to check the accuracy of our predictions. So first we're going to do is the accuracy using accuracy score. Then we're going to check with our predictions. So y-test has all the actual values and predictions of whatever we got from the KNN model. And now we're going to run this. Okay, so now it runs and we're going to print the accuracy. Let's see what's the accuracy coming out to be. 97.77%. It's pretty good. But let's try something else. So KNN models here, there's one thing about them. They have weights as well. So in terms of weights, so KNN model, as we know, we are choosing 5 closest points to the actual point we're trying to predict. In terms of weights, now what KNN model will do is give either each point around that point a uniform amount of weightage in terms of calculation, or the point which are closer to the point we're trying to predict will give the high weightage to that point. So for that, we'll first try out with uniform. With uniform, I'm going to run the number of I'm going to run the test and the training size again. I'm going to run this again. Then let's see. By changing it to uniform format, we see that the accuracy actually decreases out. Now I'll change it back to in terms of distance. Let's see if the accuracy remains the same or changes out. Oh, it remains the same. But if I run for another data set, let's see if it changes out or not. Damn. Oh wait, I didn't run this. Yeah. Changes out again. So with different data sets and with different accuracy and with different weightage, we can see that the accuracy always changes around with this model. So it's not 100% accurate. There are going to be some errors, but yeah, it's the most we can do with the KNN.
If there's any question for people on Zoom, we are monitoring the chat, so you can just ask.
Oh, that's not the one. Oh,
All right, so now we're going to go through a completely different algorithm, but the purpose of it is the same thing. It's to classify something. It's called the SVM classification algorithm. So the way this works, the formal terminology for this is called, support vector machine. And so if we have the data set, same as the last time. Say we have hardness and color. And we had our bananas and apples. The main idea is that we may have a new object like C located here last time. Except, how are we going to classify, or actually, never mind. In this case, C may be located here or here. How are we going to, oh, there's a bit of echo. Okay, so how are we going to look at a hyperplane that basically separates both of the objects from one another, both of the groups of objects? We could go like this and perhaps create a hyperplane that looks like that. Or maybe we could create a hyperplane that looks something like this. Perhaps we could create a hyperplane that looks something along the lines of this. And like I said, the main idea is to classify the two distinct different set of objects, like apples and bananas, using a hyperplane. So in this case, the optimal hyperplane that the machine learning algorithm would want to use would look something like this. The reason why, shown below, is because for the hardness and the color, so we have apples on the left, bananas on the right. Sorry about the color. The reason why is because there will be support vectors. So remember, the name of this algorithm is called the support vector machine algorithm. There will be support vectors that come out from here to the end of each of the apples, here to the end of each of the bananas. What that will do is create a bounding hyperplane right here and right here. And in between that bounding hyperplane, we will have our optimal hyperplane situated right here. Why is this the case? This is the case because if we zoom in right here, we get our maximum margin between apples and bananas. Basically, the distance with this hyperplane perpendicular, well, the distance of apples and bananas perpendicular to the hyperplane is largest.
What did you call the groups again? Like the cluster? Is that like a?
We call them classes.
Class?
Yeah. So does anyone have any questions here? Because this is basically the main idea of the SVM algorithm. It's to create this hyperplane that separates both classes. Any questions or no? Okay, so one final note very quickly that I want to mention is that this hyperplane can look somewhat different in a 3D situation. Let's say we have a situation where we have length, color, and hardness. And let's say we have our apples on the bottom in a 3-dimensional graph and our bananas on the top. Let's just say that we collected data that looks something different, something like this with another dimension of data. In this case, the hyperplane would look different. It would look something more like this. The reason being because now we have 3 dimensions of data, or we have 3-dimensional data. And like I said, in this case, if we had a C located here, the machine learning algorithm would say, okay, C is to the left of the C is above the hyperplane, and therefore C is actually a banana, right? Or if C was located below the hyperplane, we would just say, okay, this is another apple. And with that, we're going to go into the code.
Okay, so back to coding again. We're gonna code SVM this time. I'll just switch it now. Yeah. Okay. So this time we're gonna code SVM. For this, we're gonna import the SVM model. Let's see if it runs. 100%. Let's go. And now we're gonna make the model. So for this, we're gonna create model imports to svm.svc. So it's gonna create the model. And now we're gonna train the model with our data set. So now we have trained a model. Now let's take some predictions out of our model. Oh, it's not been shared. That's okay. So for all the Zoom people, yeah, sorry, apparently it wasn't being shared. So till now what we have done is imported the SVM model from sklearn. Then we have created the model using svm.svc. Now we have trained the model using model.fit xtrain, ytrain. So xtrain is the x values and y are the predictions. And then we are not the prediction, but the actual values. Now we're going to use this to train a model. So basically we have trained a model. Now we're going to use the model what we have trained to get our predictions. We're going to use a testing case over here. And then let's try printing out our predictions. So these are predictions. As you can see, these are Setosa, Versical, and Vajinica. And now we'll try checking the accuracy of our predictions. For accuracy, I'm going to use accuracy score again, which we already imported last time. And then we have a test data. And then we compare it with the predictions. Then let's try printing our accuracy score. Let's see how accurate we are with this model. Actually, yeah, this time I'll ask for guesses. Any guess how accurate this model will be? Anyone? We'll try running it. So 95.55%. It's not pretty accurate compared to last one. Let's try changing around the test data and the training set. Change it again. So yeah, as you know, we can by changing the test data and the training set, accuracy have actually increased. So change it around with the training set and the test data as well. It not only depends on the model. And yeah, that's it.
Okay, everybody, let's look at another model right now. Just a quick clarification. These are like not hard-coded numbers and like we cannot predict them. Everything is very random because whenever you call that train test split function, it just randomly chooses some testing data and some training data. Yes. So now, oh yeah. I mean, not really. Probably we can owe this kind of like it seems to us that this shouldn't happen, but maybe this is like this because the data size was very small and like we just had like 3 data points. So it's pretty likely that maybe somebody changed from 0 to 1 and somebody else changes from 1 to 0 kind of. So yeah, but like it's fine. Okay, now we are going to talk about something which is called KMeans. And I'm not as good in like changing colors and like handwriting as my counterpart, so please forgive me for that. Okay. A quick question. What do you guys think was the hardest part in the initial reference about the grocery store that I made with you? I kind of like tried to make that emotional kind of feeling over there, that like something very stressful is happening when we do that grocery store thing, like collection of fruits, giving it to the machine and like asking it for the data. Any guesses? I mean, just assume you're actually doing that process. What is one thing which you would not like to do? Like writing this code is like nothing, right? It's just like 6 to 7 lines. You don't actually need to even have a good understanding of this to write the code. You can just copy paste. But what's the hardest part, like the manual work that you had to do? Yes, exactly. And like that's the kind of pain point, right? Because initially we said that, oh, go ahead first. Oh, I thought this is a question, sorry. So the thing is, I just said that we want to increase the size of the sample in order to improve the accuracy. But as I increase the size, let's say instead of 150, I get like thousands of fruits. Now the pain is on my end, right? I have to actually sit down, classify those 1,000 to train my machine to ask it for predictions. So now we are going to see another algorithm. This is a part of a clustering algorithm. So now the difference is, so that firstly, let's talk about the technical term. The things that we were doing right earlier are called supervised learning. So what you do in supervised learning is you tell the machine that, okay, this is the data and this is the actual answer for that. This is another data. This is the other answer for that. However, in clustering algorithm, you just come, you dump that entire pile into the machine and tell it there are 2 possible answers. That's it. Just figure out whatever that is, just 2 possible answers, and I don't care anything after that. So that's why it's called clustering algorithm, because the machine is kind of trying to see which of the things are associated in one cluster, which other thing is a part of other cluster. So if I like kind of try to draw a general figure, how should it look like? Like definitely this is my color, this is my hardness. We know that something of like, we are pretty sure we'll see some sort of cluster, because we know that the more red something is, the more likely it's an apple. The more yellow it is, probably this is yellow, or and like this is red. And then this is soft and this is hard. So all my bananas would be somewhere over here and my apples somewhere over here. So I just give all these data points to my machine now, and my task is now the machine's task is now to kind of distinguish that anything that lies in this region would probably be apple and the other thing is banana. So just to write a few things up, the input that I'm giving to my machine for this algorithm, I'm giving it K. Over here, the algorithm's name is KMeans. So this K basically means how many things do we want to like distinguish between. Like for apple and banana example, we had 2 things. So K would be equal to 2 there. And then we just give it our data points and like nothing else, no other information. Now what the algorithm basically does is it creates centroids, and like the initial values of centroids, like we're pretending like we want to find the centroids, but currently we are choosing some random K data points and just calling them as centroids. So basically initially, let's say this was my data, something like this, and my K was equal to 2. So my algorithm would randomly choose 2 data points. So let's just say I'm choosing this triangle over here and this triangle over here, and my algorithm is like, oh yeah, this is my centroid and this is like my current level of prediction. So now what will happen is, what the machine would do, it will find the distance of this point from all the points that are near it. So for each of these points, like for this particular point, it will see if this is closer to this one or this is closer to this one. And I can maybe call this as my centroid 1 and centroid 2. And then it would say, if this is closer to this one, let's call this as a part of cluster 1. Let's say we are talking about this one. It kind of seems to us that this is closer to this centroid, right? basically what I'm trying to say is this one is closer to this centroid. So we'll call this as a part of cluster 2. And like, it's very easy to do this task. Like it doesn't actually have to manually do this. We all know that, okay, wait, let me ask this. All the points that are at equal distances from these two lines, where do you guys think would all those points lie? I mean, it's a high school geometry problem. All the points at equal distances, 2 points. No, it's circle is like locus of a point that is at a particular distance from a other point, right? What my point is, let's say this is a point which is at equal distance from this one and this one. This is another point which is at equal distance from this one and this one. So if I collect all those points, what would I get? I mean, I drew a very good diagram, I guess. Not really. I mean, okay. How about now? This is also very, very close. Like these distances are equal, and this distance is also equal to this. I have like 4 points like this. Which geometric figure can I talk about? Don't look at this. I'm just drawing this and this to show that the lengths are equal. It's a line. Exactly. We learned in high school for this day that a line that is perpendicular bisector of the line joining these 2 points, any point over here is equal. Anybody wants a proof? I mean, just to have revision of high school, right? I mean, this is the perpendicular bisector, right? So this is 90-degree perpendicular bisector. So this length is equal to this because it's bisecting equal lengths, and this is the same side. And we learned in high school that right angle hypotenuse side gives you congruent triangles, due to which this length is equal to this length. So all those points lie over here. I mean, okay, sorry for that math deviation, but yeah. So now what my algorithm basically does is, these were my points. It randomly chooses like 2 centroids, say here and here. It will draw a line over here, make its perpendicular bisector. And now the thing is, it will find out the centroid of all the points that are present to the left of this line, like the centroid of all these, and the centroid of all that are present to the right of this line. So we'll get some new values of centroid, and let me try to change the color. And let's say I get a new centroid over here and new centroid over here. Now my algorithm would repeat this process. It will again create a line. It will find the perpendicular bisector of this one. And now it has some new data points on this end and some new data points on this end. And it will keep on finding the centroids. Till when will it do the same thing? It will do the same thing till there's no change being observed. It kind of seems to us that we started with something which wasn't as good of separation, and actually we got something which is nearly good of a separation, right? Is that kind of, are you guys thinking I'm trying to play with you, or does it seem that this is kind of the actual truth? Yeah.
What's the difference between this and SVM? What's the difference between this and SVM?
So in SVM, what you're trying to do was you're trying to like make hyperplane. So basically the thing is, SVM was kind of very different, because in SVM, all that matters is these points. And in SVM, you already told the machine what the actual label was.
Oh.
So you are not trying to distinguish the clusters kind of thing. Like we have clusters, but like we already told the algorithm that, oh, this is the label, this is the label kind of thing.
Okay, this is like unsupervised.
Yeah, this is unsupervised learning. Does that make sense to everybody? Zoom people? Okay, I mean, now we can see the coding for this. And oh, sorry, a quick fact. Out of all the clustering algorithms, you might think that's very simple and like not as advanced as other clustering algorithms, but this is like really blazing fast, and like it's said that it's faster than almost all other clustering algorithms. And if you guys know about Big O, if you have taken something like Big O is basically kind of a measure of how fast an algorithm is. So the Big O for this algorithm is measured by number of iterations times the number of clusters times the number of instances times the number of dimensions. And as I go over here, my handwriting deteriorates. So this is something which you cannot predict, because basically you'll repeat that, because we'll have random points. And like like over here, I just showed you that, oh, the first change gave you the best one, but probably you'll not get it in the first run itself. And then this is basically, you're kind of trying to find the distance from each point. So it depends how many clusters you have, how many total examples that you have, and how many dimensions that you have. Yep. Now we can see the code for that.
Thank you, Professor Cham. All right. Yeah. Hi guys, I'm Jay again. I'll also, like Cham said, I will be typing KMean code. So yeah, like Yash did in previously, we will be first import the sklearn dot cluster and import KMeans. So yeah, for this, we're basically importing model to our code so that we can use. And it's pretty much similar, but we're gonna declare our model, basically telling computer that we're gonna use this KMeans model. And if you remember, we have to specify how many clusters that we want to find out. So we will be telling that by setting this parameter to 3 and clusters, number of clusters, right? And we're basically saying there will be 3 clusters, so please identify those clusters. And we will be separating train and test data again. But this time, we will not going to specify for Y train. And this is because like Sham mentioned, this is not, we don't have the answer for when we train, right? The model will be do it by themselves to find classes. So we will basically, like you can see from here, we'll underline, which in Python, it means we discard whatever the data that goes into. So we will be discarding the X train that we used to have in the previous examples. And yep. So yeah, like we did before, we're gonna put 30% of total data into test and left over to the train. So yeah, so now we got our models. So we're gonna use X train to train our K-mean model. Yep. It's fine. Yeah. So you can just keep using it. You're not gonna use X Y train anyway, but just to prove, I just did it again. And we're gonna feed X train data only. Again, we were not giving the answer for label for train data. And yeah, we just done with training our KM model. And now we're gonna check for accuracy. Let's do km.predict. And we're gonna give X. We want to confirm the accuracy, so we need the test data label for test data, right? So that's why we kept the Y test in here. So after we get our prediction, okay. So we want to have the accuracy. So pretty much same way, we're gonna use accuracy score that we should already imported by giving Y test and prediction that we have got. Prediction, yeah. And just And yep, by doing this, it shows 0.5333, and it's 53%. And you may notice it's really low. And this is because when K-mean run, all the 3 clusters in the beginning will be placed in randomly. So there is a pretty high chance those centroid, those dots will be placed in in a bad way that will ruin whole stuff. So yeah.
How would you determine the labels for the different classes?
So labels will be those clusters, right? So if the dots belong to one of those clusters, then that will be, the label will be specified as that.
In our prediction array, what do those numbers mean? How do you know which thing what?
Oh, so so what we want to know is which cluster does it belong to. We don't need to know about what that cluster indicates, right?
It's not useful if you don't know what. How would you derive meaning in that prediction? It's like I looked at the prediction, it's just 1, 1, 2, 1, 0. How do you know what that represents?
So for in that case, we can feed some test data, right? So because we know test X test and X, that label for that test data, right? So if we feed that test data, and if the label came back, then we can compare with the label and see which that cluster belongs to, right? So yeah, back to accuracy story. So it's pretty low accuracy. Like we cannot believe 50% model, right? And as I said, this is because the centroid is placed randomly in the beginning. So there's actually a high chance to get weird accuracy. So to fix this, the solution is pretty much easy. We're gonna run the whole model again, so that centroid will be placed in random way again, and we are resetting everything. And so we're gonna run this code again, right? And fit, and do prediction, and run accuracy again. And yeah, again, it was placed bad again. So we will run everything again. Yeah, we got 84% accuracy. So yeah, the downside of this K-means model is as I showed you, it's sometimes pretty much random, and you have to run several times and get the best model from there. Okay, there's one way to plot this by using the centroid. We got this model will give us centroid by typing cluster centers. This will give us basically the plot for centroid, and there should be 3 because we specified to have 3 clusters. And I'll just type the codes to plot these. Yeah, sorry for long code, but when you type in this way, it should show us a plot. Yep. Okay. And you may notice some weird stuff that even though I said this will be cluster, like you can see there are small groups over there, but it's pretty much random. Oh, these colors are basically representing the labels, right? And this is because we printed out in 2D, but if you remember, this data set had 4 elements. Basically, it should be in 4 dimension, but that is not possible to print it out. So I just print it as a 2D just to, give some basic idea. But yeah, if we were able to see in 4D, this should be in different clusters pretty much. Yep, that's all for me.
Okay, just a quick clarification. If anybody of you are still like curious of like how this model is kind of important, maybe change the data set to something which has just 2 labels, run the code. If you get a low accuracy, that basically means that what your prediction had as 0 and what your prediction had 1, the model actually switched it, because model doesn't know, right, which one is apple, which is banana. It's just saying, okay, I'll call this cluster as 0, this cluster as 1. So that's how you can figure it out. And that's what he was trying to say, that we already have our training data. So we can look at our training data and test on those values to see which one the model gave, like as 0, 1, or 2 over here. But preferably it would be like very easy for something which has just 2 labels, because you can just do 1 minus the other thing to get the accuracy. So if you see like 0.2 something, the accuracy is kind of 0.8 if you have like 2 labeled data. Okay. So are you guys kind of tired with apples and bananas? Like a lot of apple banana things from the beginning. We'll talk about the last model. And this is pretty much something that everybody, all machine learning enthusiasts should know. And who's going to guess the name for me? I know we are running a little late. I'll try to do it. Yes, exactly. Linear regression it is. So till now, what we have been doing is we were talking about mainly classification problems, like classifying something. But now we are actually going to predict something which might seem like more fun, and it is a lot more fun. So let's say we have something like the area of a house and the price for which the house is being sold. So I have area of house over here and the price over here. So basically what linear regression does is, as it is very clear from its name, linear, and we know the equation of a linear line, which is basically y is equal to mx plus c, where m is the slope of the line, c is the y-intercept. So basically what this model tries to do, it tries to fit the data with respect to a linear line. We all might have done this thing in geometry of finding line of best fit. That's pretty much what the algorithm does. There's a term called R square, like those all things which like it uses to find the line of best fit, but we don't need to like go into that detail because we already did like congruent triangles and everything. So let's just not go into the mathematics part. So maybe my data looks something like, and it's pretty obvious that as the price of the area of house increases, the price also increases. So now what the algorithm is trying to do is it's trying to find linear lines which best fit the data. And we all have an intuitive sense what best fitting means. Let's say this is line number 1, this is line number 2, and this is line number 3. Can somebody tell me which one do you think is the better fit? Also Zoom people. Like which one fits all the data best? Line 3, right? And why do you think this is line 3? Is that the actual reason? Like maybe I have something like going over here and something so far like this. Now none of them pass through line, but you would still say that this is the best. Kind of, yeah. So basically what your mind is saying is that like how close are these points to this line? The closer these points are, that's the better line. And there's a statistical term called R square which we use. So the more the R square, the better the line of best fit, and the smaller it is, the smaller the line. So once we have this line, we can just see like 2 points, right? I can say x1, y1, and I can find x2, y2. And the equation of my line, I can write as y minus y1 upon x minus x1 is equal to the slope, which is like y2 minus y1 upon x2 minus x1 times x minus x1. This is like normal equation of line using points, and yeah. So once we have this, we will get an equation, something like y is equal to ax plus b. Whatever x you want to predict the value for, just put your x, you get a y, and then you get your result. And that's the code that we're going to see right now.
Okay, time for coding. Oh, sorry, which one is it? Okay, now first, so yeah, basically, like Sham mentioned, this is not the classification model, but the prediction model, right? So we cannot use the iris data set that we just used until this point, because that is to classify which type of flower is that. So we're gonna use this house data set, which is a data set. So one of the sklearn data set library, and it is called California. And we're going to separate data set into X and Y. And just to see what is included, we're gonna check from the shape like we did in the beginning. And
Yeah, the latter.
oh yeah. Yeah, so as you can see, like last time we had like 150 data set, and now we have 20,640. And that will be basically number of data sets. And each data, there are 8 elements. And these elements are, so from the lab, that basically the lab that collected this data, they're saying that these elements are like median income in this block of area, or like median house age, or number of rooms, something like that. So those are 8 values. So for example, when we like print one of the element of X, yeah, so these are basically the numbers. So if I remember correctly, the third one is the age of numbers. So the 0th data has 6.98 years. Okay, and we're gonna also see last time when we print target names, it was 3 kinds of flower names, but can you guys guess what we'll have this time?
Just continue with any guesses.
Yeah, I mean, anyway, what we will be having is mid-house val, which is just a value, just a label of the data of Y, right? And so when we look at one of the label in Y, this number basically it is a value of the house in California district, one of the California districts, and it is expressed in hundreds of thousands of dollars. So it's basically a price, right? So now we're finally moving into making a linear model. Again, from sklearn, import. Now we're importing the linear model, linear regression this time. And linear regression, go to Okay, so this is pretty much same as before. We are declaring that we're going to use the linear regression model. And this time we don't have any input at this point because we don't have to specify like number of clusters or like something like that, right? And we're gonna, because we imported data, we have to separate the data again. And the test size, same as before, just 0.3. And so we are now give all the test train data and feed the model. So we're basically giving all the plots in train data, and that will make a line like Sham showed. And to predict the values, you're gonna use that linear regression model. And we're gonna input X test data. So basically those 8 elements. And by inputting those 8 elements, it will refer to the line Y value of the line, and it returns that value. Yeah. So the problem now is that it is hard to measure the accuracy in this data because it's not anymore classifying the data, right? We are predicting the value. So to compare that, what I did was I measured the difference between actual house price and a prediction and just average them. So what I did was using test and prediction, and I subtracted everything, right? And just to erase all the plus or negative signs, what I did was I squared everything and square rooted again, so that we can eliminate all these signs. Right? Oh, sorry, we didn't import. We have to import this NumPy library. Basically, it does math for you. And so to get the average, we're gonna divide all the sum of all this difference by the number of test data set that we input, which is just first dimension of diff, and print that as oh yeah, sorry, correct that. Yeah, basically we got 0.52, and if I remember correctly, all the price was like from the range of 0 to 5. So we can now tell this difference is pretty much small considering all those huge data set. that we got.
Sorry everybody for like exceeding the time limit. Thank you very much for being with us all throughout. A quick summary. So we talked about what machine learning is, how is it different from artificial intelligence. We did cover 4 models. We talked about classification, we talked about regression, we talked about supervised learning, we talked about unsupervised learning, and I am hopeful that the workshop was of much use to you all. Don't forget to stay with us this Saturday. We have another workshop for in-person people, also in 106, 4 to 5 p.m. And for people on Zoom, the same link. Try to come in person if you can. And we'll be talking about neural networks, things like fitting, overfitting, underfitting. We'll also talk about what's the difference between MLP classifier and CNN, the convolutional neural networks. And then we'll use MLP classifier in order to make our own handwritten digit recognizer. Now I'll like to invite the president of GDSC, Aditya Ravi, to give us some very exciting news. Cheers. And yeah, if you guys have any questions, we are still here. Feel free to ask in the chat, and in-person people can ask us here only. Yeah.
All right, everyone. I know it was a long workshop, but it was amazing, and I mean, I definitely learned a lot. Anyway, so have you all heard of SACAX before? All right, yeah. So for those of you who don't know what SACAX is the first major intercollegiate hackathon in the greater Sacramento area, and unlike traditional hackathons, we have a little bit of a focus on entrepreneurship as well. And essentially, the news that I want to give right now is that we are hiring for people to help us with organizing SACAX 4. And SACAX 4 is going to happen in October, the weekend of October 15 to 16. So, the next couple months are going to be super exciting for us. And we have a lot of things planned. And one of the things that we value the most in our organization is to make sure everyone has a voice, right? Like every single person's idea counts, and you will be able to make a difference. So we have a wide variety of roles open, right? All the way from people who are focused more on the technical side with web development roles open, all the way to people who, just like running around in the day of the event, just making sure everything is just perfect. So I highly encourage you to take a picture of the QR code, go through it. And then we have, so there are a bunch of links, it's basically a Linktree link, and there are a bunch of links there through which you can learn more about SACAX, what we do. And there's also the Office applications is also linked to that. So, and there's a Discord linked to the Linktree as well. Just go to it. And if you have any questions about any of the roles open or anything else about SACAX, feel free to ping one of the officers, and we'd be more than happy to help. I am greatly looking forward to reading your applications. Any questions about SACAX? All right, perfect. Yeah, the reason why a couple of people are smiling right now is that it has basically become a meme. Every time I say SACAX, they. Do you guys want to do that? You don't? Yeah, they just. You know what? You'll figure it out. Join our team, and yeah, so that we can laugh on this together.
Is like nobody is asking any questions. That's the only.
Okay, fine. Whatever. You smile. That's what matters. All right, guys. Yeah, thank you so much for coming for today's workshop. And if you have any questions on the content related to this workshop, again, just reach out to any of us on the GDSC Discord. And if you have any questions about SACAX, you could still reach out to us on GDSC Discord, or you could go to the SACAX Discord, whatever. Yeah, and like Sham said, don't forget to come on Saturday. The workshop's going to happen also in 106 from 4 p.m. to 5 p.m. And hopefully there won't be a random class that wasn't scheduled to happening.
Thank you very much, everybody.
Thank
There's
you.
nobody here. There's nobody here.